13.8 billion years ago, something incredible happened. In less than the blink of an eye, space, time, energy, and matter all burst into existence from what exactly? A singularity? A quantum fluctuation? Nothing at all. That moment, what we now call the Big Bang, wasn't just the birth of stars and galaxies. It was the beginning of everything. Temperatures soared to unimaginable levels. Particles collided in a cosmic storm. The fundamental forces of nature were still separating, shaping the destiny of the universe in mere fractions of a second. In this video, we'll journey back in time to the very beginning, to the chaotic first second after the Big Bang. We'll uncover how the universe evolved from an incomprehensibly hot and dense state into the vast cosmos we see today. From mind-bending physics to the echoes left behind in the sky, this is the story of how it all began. Despite the name, the Big Bang wasn't an explosion in space. It was an expansion of space itself. There was no blast, no shockwave, no center. Instead, the entire universe, every particle, every bit of energy, was compressed into an unimaginably dense, hot state. And then, in an instant, space itself began to stretch, not into empty space, but creating space as it expanded. So what caused this sudden expansion? The truth is, we don't know for sure. Some theories suggest it was triggered by quantum fluctuations in a vacuum state. Others propose a spontaneous event governed by the laws of quantum mechanics, where nothing can give rise to something due to uncertainty at the smallest scales. But what we do know is that time and space, as we understand them, began at that moment. Before the Big Bang, our current physical models break down. There was no before in the traditional sense, because time itself didn't exist. Within the first trillionth of a second, the universe expanded exponentially in a process known as cosmic inflation. During this brief period, the universe grew faster than the speed of light, not because anything traveled through space that fast, but because space itself was stretching. By the end of inflation, the universe had grown from subatomic to something about the size of a grapefruit, and it did this in a mere fraction of a second. The energy driving inflation then began converting into particles and radiation, giving birth to the familiar matter that would later form stars and galaxies. This is where our journey into the early universe truly begins. But what happened next? What did the universe look like after that first instant? Let's take a closer look at the timeline of the first second after the Big Bang. The first second of the universe's existence was one of the most violent and chaotic periods imaginable. In this single moment, the laws of physics were being written, particles were forming, annihilating, and forming again, and the foundation for everything in the cosmos was laid. Let's break down that first second. 10 to the negative 43rd seconds. The Planck era. This is the earliest moment we can talk about with any confidence, but it's also the most mysterious. The universe was unimaginably small, possibly as small as the Planck length, and hot beyond comprehension, with temperatures exceeding 10 to the 32nd Kelvin. At this point, gravity had not yet separated from the other fundamental forces. To understand this era fully, we'd need a theory of quantum gravity, a fusion of quantum mechanics and general relativity, which we don't yet have. 10 to the negative 36 power seconds. Inflation begins. The the universe begins expanding exponentially faster than the speed of light. This process smooths out any irregularities and sets the stage for a uniform cosmos. Quantum fluctuations during this period are believed to be the seeds of galaxies. 10 to the negative 32nd power seconds, inflation ends. The universe is now roughly the size of a grapefruit. The enormous energy that drove inflation converts into a hot soup of particles. This is sometimes referred to as reheating. The universe is now filled with quarks, gluons, and other elementary particles. 10 to the minus 6 seconds. Quarks combine. Temperatures are still in the trillions of degrees. Quarks begin to bind together to form protons and neutrons, the building blocks of atoms. At this stage, matter as we know it is just beginning to take shape. 0.01 seconds. Neutrinos decouple. Neutrinos, tiny, nearly massless particles, stop interacting with other particles and begin traveling freely through the universe. These relics of the Big Bang are still detectable today as part of the cosmic neutrino background. 0.1 seconds. Antimatter annihilation. For every particle of matter, there was an antiparticle until something tipped the balance. For reasons we don't fully understand, matter slightly outnumbered antimatter. As they annihilated each other, this tiny excess of matter survived, and it's what everything in the universe is made of today. 1 second, the universe cools to 10 billion Kelvin. By the end of the first second, the universe is still a dense, hot plasma, but it's starting to stabilize. Protons and neutrons are now abundant, and the universe is primed for the next major event, the formation of atomic nuclei. This single second set the stage for everything that followed, from atoms to galaxies to life itself. But the universe was still far from transparent. The next chapter in this story involves light and how the cosmos eventually became visible for the first time. For hundreds of thousands of years after the Big Bang, the universe remained a seething, opaque fog. Light existed, but it couldn't travel freely. It was constantly scattered by charged particles in the hot plasma that filled space. The universe was, quite literally, in the dark. But all of that changed roughly 380,000 years after the Big Bang, during a momentous event known as recombination. At this point, the universe had expanded and cooled enough, down to about 3,000 Kelvin, for protons and electrons to combine and form neutral hydrogen atoms. This seemingly simple act had profound consequences. It allowed light to finally travel unimpeded through space. This moment is when the universe became transparent. The light that was freed during recombination still exists today. We know it as the cosmic microwave background, or CMB. It's the oldest light in the universe, stretched into the microwave spectrum by billions of years of cosmic expansion. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, the CMB is one of the most important pieces of evidence for the Big Bang theory. The CMB isn't uniform, though. It has tiny temperature fluctuations, just a few parts in 100,000, which represent the seeds of structure in the universe. These slight variations in density eventually led to the formation of galaxies, stars, and everything else we see today. In this era, known as the photon decoupling era, the universe finally had structure. The fog lifted. The cosmos went from being a glowing plasma to a dark, vast expanse scattered with slowly forming clumps of matter. This also marked the beginning of the cosmic dark ages, a period lasting hundreds of millions of years, where the universe was filled with neutral hydrogen but devoid of stars and galaxies. It was a time of silence and darkness before the first lights of the universe would flicker into existence. So how did we get from this cold, quiet void to a universe filled with stars and galaxies? After recombination and the release of the cosmic microwave background, the universe entered a period known as the Cosmic Dark Ages. No stars, no galaxies, just cold, neutral hydrogen gas spread across a rapidly expanding cosmos. But even in this darkness, gravity was quietly at work. Over millions of years, tiny variations in density, those same subtle imprints in the cosmic microwave background, allowed gravity to pull matter together into increasingly dense clumps. These clumps grew into the first cosmic structures, dark matter halos, invisible scaffolding that would soon cradle the first sources of light. Roughly 100 to 200 million years after the Big Bang, something extraordinary happened. Deep within these dark matter halos, clouds of hydrogen gas collapsed under their own gravity, compressing and heating up until nuclear fusion was triggered. The first stars were born. These weren't stars like our sun. They were massive, hot, and short-lived, hundreds of times more massive than any star today, burning their fuel rapidly and dying in violent supernova explosions. They're known as population 3 stars, and they played a vital role in shaping the early universe. Their intense ultraviolet radiation began to ionize the neutral hydrogen around them, slowly ending the cosmic dark ages and initiating a phase called cosmic reionization, a transformation that made the universe transparent once again, this time to starlight. But these first stars didn't appear alone. As more stars formed and grouped together under the influence of gravity, they assembled into the first galaxies. These early galaxies were small, chaotic, and full of rapid star formation and supernova activity. Despite their size, they were the building blocks of everything we see in the universe today, from majestic spiral galaxies like the Milky Way to the giant elliptical galaxies at the cores of clusters. The deaths of these massive first stars also seeded the universe with heavier elements, carbon, oxygen, iron, ingredients necessary for planets, life, and complex chemistry. Before these stars, the universe was made almost entirely of hydrogen and helium. Their explosive ends enriched the cosmos and set the stage for the second generation of stars, ones more like our sun. The birth of stars and galaxies lit up the universe for the first time, breaking the darkness and igniting the complex evolution of cosmic structure. But these were just the first sparks. What came next would shape the grand design of the universe we see today. As the first galaxies formed and grouped together, the universe began organizing itself on a much larger scale. Over billions of years, gravity continued pulling matter into increasingly complex structures, sculpting a vast and intricate architecture known as the cosmic web. This cosmic web is the largest structure in the universe, a network of filaments, clusters, and voids that stretches across the entire observable cosmos. Imagine strands of a spiderweb spanning hundreds of millions of light years, with galaxies clustering along the filaments, superclusters forming at the intersections, and enormous voids in between, where almost nothing exists. These structures were seeded by tiny quantum fluctuations that were amplified by inflation and shaped by the interplay of dark matter and gravity over time. Dark matter, though invisible, plays the starring role in this drama. It acts as the gravitational glue that holds galaxies and clusters together, guiding the overall flow of matter into these grand formations. Galaxies didn't just float randomly in space, they followed the gravitational contours of this web. Where the filaments intersected, matter collected into vast clusters of galaxies, held together by mutual gravitational attraction. These clusters can contain thousands of galaxies, surrounded by superheated gas and permeated by dark matter halos. Meanwhile, the spaces between these filaments, the cosmic voids, grew ever larger. These vast empty regions span hundreds of millions of light years and contain very few galaxies. They're not completely empty, but compared to the rich clusters along the filaments, they're like cosmic deserts. Over time, this large-scale structure became more pronounced. Galaxies merged, formed clusters, and settled into more stable orbits. Spiral galaxies like the Milky Way spun into graceful shapes, while massive elliptical galaxies formed from countless collisions and mergers. By a few billion years after the Big Bang, the universe had transformed from a nearly uniform sea of matter into a highly organized, dynamic system, full of complexity, diversity, and motion. And in one quiet corner of this immense web, something remarkable began to happen. A solar system formed around an average star in the outer arm of a modest spiral galaxy. That system would eventually give rise to life, and curious beings who would one day look up and ask, where did all of this come from? But before we get to us, there's one final chapter in the origin of everything we see today, the birth of our sun and the solar system. Roughly 9 billion years after the Big Bang, deep within one of the spiral arms of the Milky Way galaxy, a cloud of gas and dust, enriched by countless generations of dead stars, began to collapse under its own gravity. This collapse would eventually form a yellow main sequence star, our sun, and everything that orbits it. The region where our solar system formed was part of a dense molecular cloud, full of elements like carbon, oxygen, nitrogen, iron, and silicon, the building blocks of rocky planets, and ultimately, life. These elements had been forged in the hearts of ancient stars and scattered across the galaxy by powerful supernova explosions. As gravity pulled this cloud inward, it began to spin, flattening into a protoplanetary disk. At the center, pressure and temperature soared, igniting nuclear fusion. And just like that, a star was born. Around it, in the swirling disk of debris, tiny dust grains collided and stuck together. Over millions of years, these clumps grew larger, forming planetesimals, then protoplanets, and finally, full-fledged planets. Closer to the Sun, rocky planets like Mercury, Venus, Earth, and Mars took shape. Small, dense, and built from metal and stone. Farther out, beyond the frost line, the giant planets, Jupiter, Saturn, Uranus, and Neptune, grew massive by accumulating gas and ice, forming the gas giants and ice giants we know today. Leftover debris became moons, asteroids, and comets, remnants of the early solar system still floating through space. Amidst all this, one planet, Earth, formed at just the right distance from the Sun. It had the right ingredients, a stable orbit, and eventually a dynamic atmosphere and flowing water. These conditions made it a unique cradle for something truly extraordinary: life. The Sun's formation marked a quiet but monumental turning point in cosmic history. From the ashes of dying stars and the chaos of interstellar clouds came a system teeming with complexity and eventually consciousness. We are, quite literally, made of stardust. the product of cosmic processes set in motion billions of years ago. Our existence is not separate from the story of the universe. It is a continuation of it. The story of the universe is vast, complex, and still unfolding. From the Big Bang to the formation of stars, galaxies, and ultimately life on Earth, each chapter in this cosmic saga is connected by a chain of cause and effect stretching back nearly 14 billion years. But this isn't just a story about particles, gravity, and physics. It's a story about us, about how, in a seemingly indifferent cosmos, a species emerged capable of looking up at the night sky and asking, where did we come from? We are not separate from the universe. We are the universe made conscious. The atoms in our bodies were forged in stars, our solar system born from their remnants, our planet sculpted over eons into a cradle for life. And now, after all that time, we are here, able to study, question, imagine, and explore. Understanding our cosmic origins gives us perspective. It shows how rare and fragile life may be. It reminds us how much more there is to discover and how little time we truly occupy in the grand sweep of existence. And yet, in this tiny moment we call now, we have the power to shape our future, to preserve this planet, and to continue exploring the universe that made us. So, next time you look up at the stars, remember, you're not just looking at the past, you're looking at the building blocks of everything, including yourself. Join us next time as we explore more mysteries of the universe.